The United States Navy, through the Chief of Naval Operations, Deep Submergence Directorate, and the Commander of Submarine Development Group 1 are chartered to conduct deep submergence operations. Today, the United States Navy can reach some 98% of the ocean floor thanks to deep submergence vehicles. But it wasn't always like this. On December the 16th, 1961, Trieste, the Navy's first submersible bathyscape, reached 35,800 feet, the deepest man has ever gone. In 1970, the Navy commissioned two DSVs, Turtle and Seacliff. Deep submergence vehicles, or DSVs, have enabled the Navy to sharpen our skills in ocean search, location, and recovery. DSVs are also capable of supporting scientific research. The DSVs Turtle and Seacliff are based at the Deep Submergence Unit, located on North Island Naval Air Station, San Diego. The North Island base is ideal because of its convenient proximity to both the ocean and an airfield. This gives the DSVs flexibility in the method of transport to a mission. When a DSV reaches the ocean floor, it is subjected to extreme pressures. This cup, exposed to sea pressure at 20,000 feet, was compressed to a fraction of its former size. To survive these pressures, special materials and construction techniques are used to build the DSVs. Seacliff and Turtle are nearly identical, both in the materials and in their design. Because of its titanium hull, Seacliff has a greater design depth. Turtle, on the other hand, uses HY100 steel for its control sphere and can reach a tested depth of 10,000 feet. The DSV uses a weight system to help achieve its desired depth. When the DSV is ready to dive, the ballast tank is vented and fills with water. In addition to a ballast tank, the DSVs carry weights. DSVs use weights like helium balloons use sandbags. After the ballast tanks have been vented and filled with water, the vehicle will start to submerge. To slow the dive rate, descent weights are released. Once the vehicle is at its desired depth, selective weights may be dropped or variable ballast added to attain neutral trim. When the DSV is ready to surface, the ascent weights are released. The ascent and descent weights are located on the side of the vehicle. The selective weights are located towards the bow. Although both vehicles use selective weights, Turtle does not have the ascent and descent weights. Turtle uses its side pod propellers to reach its desired depth. Batteries are located in the aft section of the DSV. These batteries power the vehicle. At its maximum speed of 2½ knots, power can be provided for 8 hours with the current silver zinc batteries. At a cruising speed of 1½ knots, the DSV can operate up to 20 hours. The Mercury trim system maintains fore and aft trim. The trim system has 4 spheres. Ballast is shifted between the spheres to maintain the DSV's trim angle. A special filler called syntactic foam is form-fitted into any remaining open spaces. Syntactic foam is very buoyant and is specially designed to withstand tremendous pressure without losing its shape or absorbing water. The syntactic foam is made of glass microspheres bonded by epoxy. It is cut into different shapes to conform to spaces between installed equipment, like pieces of a puzzle. The outer skin is made of glass reinforced plastic, or GRP. Its texture closely resembles fiberglass.
Inside, outside, ready to train a pod. Train a pod clockwise. Train a pod clockwise,
The DSVs are equipped with 2 side pod propellers. These propellers are used to maneuver the vehicle during the dive, as well as to drive the vehicle to its desired depth. They also provide directional control. The stern propeller is used to move the DSV once it has reached its desired depth. The propeller also helps to steer the vehicle. DSVs use continuous transmission frequency modulated, or CTFM, sonar. This high-resolution sonar is used for search and obstacle avoidance. It has a range of 1,500 yards. A 35mm camera and a pan and tilt video camera are used to record mission events for later study. 3 viewports allow the occupants to observe their external surroundings and aid in piloting the vehicle. Pictures can be taken through the viewports with a handheld camera. While the DSV is a valuable tool to scientific research, its primary mission is search and location. After locating an object, the DSV can perform useful work or retrieve objects using its grasping manipulators. The crew of the DSV are experts in using the manipulators. DSVs have been used to recover aircraft parts and other large objects. The manipulators are also designed to handle fragile objects. Each DSV is equipped with 2 manipulators. Different tools may be required for different missions. The manipulators can be equipped with a drill, cable cutter, parallel jaw, or twin scissors. Baskets in front of the DSV can hold recovered objects. If the DSV cannot lift an object due to its shape or weight, the manipulators will attach a cable to it. Once the DSV surfaces, the cable is attached to the support ship. The support ship can then reel the object to the surface. Emergency oxygen is available in case of fire or other unexpected life support problems. In the event of a casualty, certain external equipment can be jettisoned via explosive bolts. This will free the DSV and/or provide positive buoyancy. These casualties might include flooding, fire, or entanglement.
Sound check. How do you hear me? Over.
Inside, outside, where are you?
It takes teamwork to move the DSV to the mission site. First, the DSV is loaded onto a land transport vehicle, or LTV, a specially designed trailer. The LTV can transport the vehicle to either the adjacent airfield or to a pier. The roads must first be checked to ensure that they can accommodate the height, width, and weight of the LTV. One C-5 jet or two C-141 aircraft can transport the DSV, LTV, equipment, and crew to a pier at a distant location. The DSV can be readied for airlift in less than 24 hours. The DSV rides to the dive site on the Laney Schwest, a specially modified support ship. The crew makes extensive pre-launch checks before the mission dive.